equals Kc times RT to the delta N power, delta N of gas. Something about this problem is very, very convenient. What's convenient? What about it? The delta N value is 0. Right. Delta N is 0. What does that mean then? Yeah, these two are equal to each other. Yep. That is the rare case. That's not that rare even, I guess, but when you're talking about chemistry problems, it'll be rare because it's so easy. I wouldn't give you 15 easy questions. Why would I, right? So anyway, this is the case where Kp and Kc are equal to each other if you have the same number of moles of gas on both sides. So what's the answer to number 10? A. Right, you were given Kc. Kp is the same thing because your delta N is 0. So A would be the Kp. All right, so that was a kind of a gimme. That was a softball. Now, let's see if we can do number 11. In number 11, you're given two reactants. Somehow, when they were typing this, they missed the plus sign between the two reactants. So you got CS2 as a gas, and then you got 4 H2s as a gas, yields CH4 and 2 H2Ss. So remember what I said about if they don't specify which K value? Look at that. It says the equilibrium constant K is 0.28. But they mean Kc. Because if they don't tell you, they mean Kc. And then what is Kp at the same temperature? So would you try that one? Oh yeah, make sure that your temperature is in Kelvin. Yep. Because you got to be consistent with R. And anytime you see T, if it's not a delta T, you need to use Kelvin. It's a pretty simple exercise. I mean, it's not as easy as counting to 4, but it's not any challenge for you, I don't think. Unfortunately, this would, maybe it's not unfortunate, this would not qualify as a good multiple choice question because the math is not any way mental math. And look at the choices, how close they are to each other. When you have a mental math multiple choice question, the problems usually have the answer choices spread real far from each other. What do you get for number 11? You get C? You got a question? Oh, because the delta N is the products minus the reactants. Product coefficients minus reactant coefficients. So it's 3 minus 5. We all good? All right. Now the next question I'm going to ask is number 13. However, well, we can take a look at number 13. It's not just a here's Kc, find Kp question. Number 13, something new comes up. So it says the Kp value is 1.8 for this reaction. And you can see a very simple chemical equation, all ones for coefficients. So, sufficient PCl5 is put into a reaction vessel to give an initial pressure of 2.74 atmospheres at 250, which is what we have the K value for. Calculate the pressure of PCl5 after the system has reached equilibrium. So PCl5 is the reactant here, And it's going to react, and it's going to break down and make those two products. Would we be able to calculate how much PCl5 is there at the end? Well, we're going to have to. That's what the question is. So there's got to be a way to do this. Anytime a problem will give you how much you have to start with, and if it asks how much you have at the end, how much is there left at equilibrium, I want you to create what we call, an ICE table. Now, your chemistry world is about to change drastically. This idea of an ICE table, today here on December 17th, you're going to do your first ICE table. By the time we're through February, you will have done probably at least 150 ICE tables. Ooh, man. Maybe more. I don't know. Maybe you'll do 200. I wish we could count. I don't think anybody's going to want to count. ICE table is not like, if you think, oh, ICE table, does that mean like Cold Stone, where you got this real cold table? No, it's not like that at all. That'd be nice. It has nothing to do with frozen water. ICE stands for these three things: initial, change, and equilibrium. It's a way that we're going to stay organized in solving equilibrium problems. And you know, I kind of joke about ICE tables as if it's something that I'm kind of laughing at you for having to take on. But it turns out ICE tables, nobody complains about them because they're kind of nice. They help us stay organized. It's just one of those tools that we're going to use. And you're not going to mind using it. Now, into my ICE table, I put 2.74 atmospheres. That's the pressure of PCl5 that the problem says we're going to put in. This is how much we're starting. I presumptively put in 0 for the products. And it's an okay assumption because the problem doesn't say anything about us having products present at the beginning. So you can always assume that you don't have any products at the beginning. That's kind of the point of a chemical reaction, is to make the products. Assume you don't have any to start with, unless the problem tells you, oh, well, there was some Cl2 already there. It would tell you that, and it would make a kind of a big deal about that. So always assume you have no products at the beginning, unless the problem says otherwise. So you can tell that the reaction is going to go to the right and produce products. What tells you that products are going to be made in this reaction? Something up here tells us that products are going to be made. What is it? What is it? Come on, you guys. It's the week before vacation. I thought you'd be full of energy. Do I need to go get the school nurse to see if you have a pulse? Shaitanya, did you have something to say?
What's the question?
Oh, what's the question? How do we know? What up here tells us the reaction is actually going to make some products? The K value. The K value does. Yeah. Is that Mitchell that said that? All right, Mitchell, you got it. Good job. The K value is 1.8. K is greater than 1. If K is greater, remember what K is. K is the products over the reactants. Were you saying that? That was right. Say it louder so I can hear you. Be bold. Come on, Sejal. So yeah, K is products over reactants. So if the K value is greater than 1, that means there's going to be more products at the end than reactants. Yes? So I know for sure this reaction is going to go to the right. It's got to make some products. So how much? How much does it go to the right? Well, we know what the ratio is at the end. So here's the way that we're going to fill out an ICE table. If I don't know anything else, but I know that the reaction goes to the right, then we can say that the PCl5 is going to go down. So I'm going to put a minus sign. I don't know how much yet goes down, but I'm going to have to solve for it. We're going to call it x. It's going to go down by some amount x. And since the PCl5 is going to go down by x, that means that the PCl3 and the Cl2 are both going to go up by x. Because it's a 1-to-1 ratio between that and that. So the amount that the PCl5 goes down is going to equal the amount that the PCl3 goes up. You with me on that? That should make sense. And the same thing for the Cl2, it's 1-to-1 with the PCl5 too. So at equilibrium, the amount that we're going to have, we start with 2.74 and it goes down by x, so we have 2.74 minus x. And that's as good as we can do for right now. We're going to have to use our algebra skills to figure it out. The PCl3 and Cl2 were 0 plus x, so we'll just call it x. All right. So what is the question asking? The question is, calculate the pressure of PCl5 after this reaches equilibrium. So this number right here, what is the pressure of PCl5 when the system is at equilibrium? Yeah? So we want that number right there. We've got to solve for x. We have a K expression. Kp equals 1.80. So 1.80 equals that times that divided by that. And there's no exponents because all the coefficients are 1. So it's going to be x times x over 2.74 minus x. Solve for x. What do you see? What are you going to have to use? X squared over 2.74 minus x equals that number. And you got to solve for x. What do you have to use? The quadratic formula. Oh boy. Here's some good news though. Some good news for some of you. These fancy calculators, the TI-84 Plus and the TI-84, the new skinnier ones, if you just go to apps, you're going to get a menu of apps.
Me too. TI-83.
TI-83. Love those old vintage TIs. But go down with your, I'm still going down. Oh, if you want French, you'll get a choice of French or German, if you like that. Netherlands. Oh my goodness, there's periodic tables even. One of your choices under apps is, I don't know, it's Polysmelt. P-O-L-Y-S-M-L-T.
Yes.
Select it. Go ahead, you select it.
Whoa, I can convert units.
Got under apps? Go to apps. And then one of them is Polysmelt. Click on it.
I would have passed.
You got everything deleted, probably by a math teacher.
Units, I
Did they clear your memory and so you're...
KPA.
I don't know how you get it back.
It's like pressure. Wait,
Why?
there's power to
Well, some last summer, so I don't have it because I got my memory. But yeah. Yeah, now, I don't know how you get those apps back because I think it's app number 8. It should be number 8. Some of you only have number 1 and that's it.
You use it.
Keep going down. One of the apps is Polysmelt. P-O-L-Y-S-M-L-T. Italian?
Yes. I don't think so.
You could. But it would be, it's available. I don't know how to get it on there though. But anyway, that is a root finder. That's so nice.
Joules.
Now let's see. Nate, you said that you hate the quadratic. Do you have one of those nice calculators? Oh. It's on there. So all you have to do is come and write it in standard form and type in the A, the B, and the C term, and it'll tell you what the roots are.
Yo, let's use some matrix.
Yep. It'll be second order. It's like the highest coefficient.
Dude, who uses matrices to solve power?
Yeah, there you go. So just type in what the coefficients are.
What are you
Grace?
I remember what that is. I don't remember what that is.
Oh, yeah.
Hello? Where are we?
What is this one?
Okay, so you go to... Okay, you go to apps, and then you go to this, and you click on the first one. I don't know how to go back.
I see your